Hi folks, this is lesson 1 of properties of derivatives. First thing we'll do is we'll look back at what we came up with last time. So we took this idea of instead of just finding the rate of change of a function at a particular point, is if we take the rates of change of a function at all the points in the domain, we can create a new function, which we called the derivative function. Okay, so let's say I'm looking for the derivative of f. So f prime at x. So this function here represents the function of the slopes of the tangents of the original function f. Okay, so what we did is we used our definition for rate of change, okay, giving it its new name now, derivative. Okay, but instead of determining the rate of change at a specific point A, we made a change and turned that into the rate of change at any point x in the domain. Okay, and so this is what we have as our definition of the derivative function. So keep in mind this is a function because as x changes, the value of the limit will most likely change, especially if we're working with a function that is not linear, where we don't expect the rate of change to be the same at all x values. Okay, so I asked you to find some limits of some common functions. So we did x squared, we did x cubed, we've done a few for homework. Let's take one more example before we move on. Okay, so if we take the example of the derivative of x squared plus x. Okay, so let's input that into our equation. So here limit is h approaches 0 of, so this function here evaluated at x plus h, so x plus h squared plus x plus h. Okay, and then minus the function evaluated at x, so x squared plus x, okay, all over h. Okay, and as before, if we actually check numerator and denominator, we see that they both approach 0. So as usual, we have our indeterminate form. So we're going to try to do some algebra here to see if we can determine the limit here. Okay, so I guess what we'll have to do is we'll have to expand. So we'll do that here. So here we've got x squared plus 2hx plus h squared plus x plus h, and then here we have minus x squared minus x. So you'll notice my very liberal use of brackets here. This is just to avoid any silly sign errors to make sure everything works out. And here things work out quite nicely because this x squared will cancel out with that one, the x with the x, and everything we're left with in the numerator has a factor of h. So I'm going to factor out that h here, and we're left with 2x. Okay, here we're left with plus h, and then here we're left with just plus 1. Okay, all over h, and as we hoped, that h in the denominator cancels out, and so we're just left with the limit as h approaches 0 of 2x plus h plus 1. Now this term here and this term here do not depend on h, so the fact that h goes to 0 does not affect these two terms, so they act like constants. Limit of a constant is just the number itself, and here this h is approaching 0, so I'm just left with the function 2x plus 1. Now there's a few things I want to say here. First of all, there's a lot of polynomials that we deal with, so we should be thinking that perhaps having to do this whole process for every single function that we work with, and you have to figure this was a pretty easy quadratic. Imagine a quartic function that has 5 terms in it, with the expanding that we have to do would take quite a long time. So as we did with limits, we're going to try to see if we can perhaps find a way to break this derivative down of this quadratic with 2 terms into a simpler form. Now I hope you'll notice here that 2x was exactly the derivative we found for the function x squared. Okay, and if you think of the function y equals x, well, the slope is equal to 1, meaning the derivative function, since the slope is constant for a linear function, just equal to 1. So we notice here that the derivative of this sum is the sum of the derivatives. Okay, so that might give us this idea that we could take a more complex function and break it down into its simpler parts. So instead of having to do this whole process, we could say, well, I know what the derivative of x squared is. I've already found that. And I know what the derivative of x is the derivative of a sum always just the sum of the individual derivatives? So this is what we're aiming for. And maybe we can do that with multiplication and division, similar to what we had with properties of limits. Okay, so what I'm going to ask you to do now, I'm going to ask you to turn off the video and do these exercises here. Okay. Now, one of the things I want you to do is I want you to prove that the derivative of a constant function, okay, so say y equals 5, well, if you think about this function here, what would the slope of the tangent be? Well, there is no rate of change. It's 0. The function does not change as x increases. So one would expect that the derivative of a constant function, but I want to do this as generally as possible, should be equal to 0. Okay, so again, you're going to use the limit definition to prove that the derivative of a constant is equal to 0. Okay, and I'm also going to ask you to prove, because we haven't done it yet, and even though it makes perfect sense that the derivative of x is equal to 1, I will ask you to actually prove that using the limit definition. Okay, so do that, and then we'll come back and start on lesson 2.